Everyone, this is Mr. here. We're going to be taking up the thermal energy quiz you just wrote. So the first question is just basic definition. The total amount of kinetic and potential energy is going to be thermal energy. Okay. So remember, heat is the transfer of energy. Temperature is the average EK. Kelvin is just a way of measuring temperature, another way other than degrees Celsius. So correct answer, thermal energy. Next one, the specific heat capacity. What does it depend on? Number one, mostly the material the substance is made of. Not the size, not the mass, or the initial temperature. That is all thermal energy, but the heat capacity really depends on the intermolecular forces. So, for example, substances with lower intermolecular forces, such as iron, don't have a high heat capacity. Water has a significantly stronger heat capacity because it has an uneven charge. So the electrostatic attraction between these adjacent molecules causes a very, very strong pull. And this pull causes much stronger intermolecular forces, and as a result, it takes more energy to increase the temperature to make the particles vibrate. So it has a higher heat capacity as a result. Next one, we're looking at different states of matter and particles for convection, conduction, and radiation, three forms of heat transfer. So for convection, it happens in fluids, so it's going to happen in liquids and gases. And what happens with the particles is they vibrate, and as you increase the energy, there's more space associated with the particles, and then as a result, the density goes down, and the particles will rise. And then when you're cooling, the opposite happens. Less energy, less space, more density. So it's all about changes in density over here. That's significant. All right. Conduction happens primarily in solids. And what happens here is the particles vibrate, and what they do, instead of moving, they can't move around, so they collide, and they collide with adjacent particles. So it's a very, very gradual process. It takes a long time for it to occur. Now, radiation happens in any state of matter, and basically, as long as the state of matter is relatively transparent to that form of radiation, there's no particles involved. Remember, it's only a form of electromagnetic radiation, so electromagnetic waves are involved here. All right, and those are the key points. Okay, next one. How about this? Why do you burn yourself on pie filling but not on the crust? This is simply because of the water content. The crust is relatively low water content. The filling is very high water content. Now what happens is, remember, water has a very strong intermolecular force attraction between adjacent molecules, and this causes there to be much, much more energy required to heat up the water. And what happens is, by the time you heat it up to the same temperature as the crust, it's absorbed a lot of thermal energy, and that thermal energy has to be released. So it takes a long time for it to be released into the environment. So the big thing here is lots more thermal energy for the same temperature, and it takes longer for it to be released. So make sure you have that link with thermal energy, quite important. All right, next one was the mixture problem. So here what's happening, we're putting water, that's hot chocolate, water, essentially into an aluminum mug. The mug is at a 21 degree Celsius initial temperature. The water's at 91 degrees, so it's hot. Remember, hot chocolate. And what's happening is the hot chocolate is going to be losing energy. So water goes, the energy goes into the aluminum. So we're making an assumption that all the thermal energy, or not all of it, but the thermal energy from water goes into aluminum until they reach the same temperature or thermal equilibrium. Then no more energy transfer occurs. So that's why we've got the loss of energy from water is equal to the gain of energy by the aluminum, and then basically negative MCAT, positive MCAT. Just be careful here with the negative, okay, when you're doing the hot side. So you have negative times TF gives you negative TF, negative and negative gives you positive. Then you collect the like terms, and you finally get your final answer of 83 degrees Celsius. Now you'll notice that the water went from 91 degrees Celsius to 83. It went down by 8 degrees. However, the aluminum went from 21 to 83. It increased its temperature a lot more. Why? Simple fact, the same amount of energy allows a greater temperature change in the aluminum because it has a lower heat capacity. And that's it. So make sure to go over this, look over formatting, and be careful with the short answer. You should be mentioning thermal energy again for the heat capacity question, and also briefly touch upon the intermolecular forces being very strong in water. That's it.